So electric power. In in physics, we define power as the rate of work done, right? Or the rate of doing work. Okay. And previously we said that work is energy, energy is work. Okay, so we can also say that power is rate of change of energy. Yeah. All right. So the rate at which the energy from the source is consumed is called electric power. So the moment we are talking about rate, that means there is a time factor in there. Okay? There is a time factor in there. Okay. Now, power, like I said, generally is the rate of doing work, and we know that work is a form of energy. Therefore, if power is work done over time, I need you to pay attention here, right? If power is work done over time, and we know that work is energy, so that means for our system or our circuit, the energy is as a result of the electric potential energy, right? Which is U, and time, which is what? T. Okay? And time, which is T. So if we, with this in mind, we can define we defined electric potential energy as the work done in moving a charge from infinity, right, to the vicinity of the charges, that the potential that we've created, right? So that is in a way a form of work done, right? Great. So if we substitute work done by our electric potential U and divide by time, then we're going to get electric potential is kq squared over d. We already defined that, times 1 over t. So I've just merely done some separation, right? And if we rearrange this, we can move 1 q from the square and put it on top of the t, so that we get q over t, and then we'll be left with kq over d, right? And remember, we defined voltage as what? kq over d. That means we have a voltage component here, right? And we also define current as the amount of charge passing a cross-sectional area per unit time. So current basically is charge per time, which is Q over T. So if we put everything together, electric power can be calculated as voltage times current. Okay, so this is where, or this is how we got electric power to be equal to VI, okay, voltage times current. Again, power, just like everything, is measured in joule per second, right? But in electrical power, we call it watt. Do we measure all power as what? I've forgotten. Oh, okay. So that is how we got power, okay? That is how we got power. Just from, so you see that everything that we are doing is on point, right? So from voltage, we came to current, then, so voltage causes current, and the combined effect of voltage and current gives us what? Power. And the mathematics is also evidently showing that, okay? I love it. Good. Now, just a while ago, we defined electron mobility as a measure of how quickly electrons move through materials in response to what? Electric field, right? Good. Now, this property actually characterizes the ease of the electron drifting through the material, okay? Take note of something here. Something is moving, and how fast it's moving. What do you think dictates how fast that thing will move? When something is moving, what dictates how fast that thing moves? All right, so let's see if we have an answer. So electromobility, as we said earlier, is influenced by temperature, impurities, and defects. Okay, this is just a recall. Everything I'm stating here is just a recall. Okay, now here is the thing. Since electromobility is a key factor in determining the electrical conductivity of material, the higher the mobility of the material, the higher the electrical conductivity. the higher the electron mobility of a material, the higher its electrical conductivity. Why? If the mobility is higher, it means more electrons will pass per unit time. And more electrons passing per unit time means high current. And high current means good conductivity. So you see how they interplay, right? Great. Now, electrical conductivity is an intrinsic property. When we say that a property is intrinsic, it means that it is by nature, right? For instance, the ability to have two legs is an intrinsic property of human beings. So if we see a human being with one leg, we will say that the person is deformed. Or a human being with three legs, we say that he's an alien. Because having the property of having two legs is an intrinsic quality or characteristics of what? Human beings. Okay, so when we say that something is intrinsic, it means that it is not affected by size, by shape, by anything. If I pick a small quantity of that thing, okay, if I pick a human being from Europe, he will have two legs. A human being from Africa, two legs. A human being from India, two legs. Right? Because all human beings by nature have two legs. That's what we mean by intrinsic property. Okay. The opposite of intrinsic is extrinsic. Okay, so extrinsic means that thing is external. So for instance, some people are tall, others are short. We can say not all human beings are not tall. Some human beings are short, some human beings are tall. And this depends on external factors. Okay. It's not property of human beings in general. It's a property of certain human beings. Okay. All right. So when we say that something is intrinsic, like I said, it does not depend on the shape or the size of that thing. Okay. So if I take copper, 1 gram of copper will have the same conductivity as 10 grams of copper. That's what we mean by intrinsic. Okay. Or a copper metal that has been beaten into a square shape will have the same conductivity as copper metal that has been beaten into cylindrical shape. The shape doesn't have any effect on their conductivity. Now, when we talk about electrical conductivity, it is measured in units of Siemens per meter. Okay, Siemens per watt meter, and this is actually its SI unit. I don't usually hear people talking about this. How many of you already knew this one? Okay. Now, take note here. If mobility talks about how fast the charges move, right? And these charges don't move perfectly, then it means that there is something that also affects how the charges move. Is that okay? Or let me put it like this. If different metals or conductors have different conductivity, then it means that if we look at it from the opposite side, there is something else that opposes how electrons flow through these materials. Is that okay? So it happens that is the case. Okay, so anything that decreases electron mobility in a material will in turn oppose the flow of current, right? Because mobility is related to electrons. It's related to current. It tells how much current will flow. So if something is reducing mobility, that thing is also reducing current. It's a consequence, right? So since materials are not perfect, mobility materials are not perfect, and it also means that every material has an intrinsic quality to oppose the flow of electrons, right? They have an intrinsic quality to have a certain conductivity. The same way, they have an intrinsic quality to oppose the flow of electrons. Now, this intrinsic quality is what we call electrical resistivity. We have added a new term. We started with voltage, we came to current, we came to power, talked about conductivity. Now we are adding what? Resistivity. Okay. Now take note that conductivity is not the same as conductance. Neither is resistivity the same as resistance. These are two different things. Okay, and I'll explain very soon. So resistivity is actually inversely proportional to conductivity, right? So as conductivity, a material with a higher conductivity will have a lower resistivity. A material with a higher resistivity will have a lower conductivity. It's basically that, right? Great. So if you take copper and aluminium, copper has a higher conductivity than aluminium. That means aluminium has a higher resistivity than copper, right? If you are taller than me, I am shorter than you. Everybody wins. All right. So again, resistivity is intrinsic. That means it does not depend on the shape or the size of the material. Okay. Now, the total. Now, please take note. You may not find this in any book because this is my own definition from my own understanding. Let me make it clear. If you take the if you take the total of all the activities and properties, right, that oppose the flow of electrons, we can bundle them up and call them resistance. If we take up all activities, talk of temperature, talk of impurities, talk of whatever, and internal properties of a material, so far as these things oppose the flow of current or electrons, that thing qualifies as resistance. So when we put all these opposing agents together, we define what we call resistance. We've added another thing, resistivity, now resistance. Okay, so look at something here. Current is a measure of the number of electrons that can pass through a conductor's cross-sectional area per unit time, right? Good. So this means that there are actually two ways we can increase current in a system. Okay, take it as we have a pathway, and this pathway is narrow such that only one person can move through the pathway, right? And we want to be able to measure 2 people passing per second. How do you think we can achieve this? We can achieve this by making those people run faster. Okay? So if it takes one person to pass in a second, if we ask them to run, we will end up having about 2 people or even more passing per second. That means we can say that 2 people pass per second, even though the pathway can allow just one person to pass at a time. Okay, remember, current is basically saying that, hey, how many number of charges passed in per second. Okay, now the second way we can increase, so this is the first criteria, by increasing the speed of the electrons, we can make electrons pass in you can make 2 electrons pass in a second instead of 1, right? And this will result in a rate of 2 electrons per second. Now, another way we can do this is by widening the pathway, okay, so that 2 people can walk side by side and pass in a second. Either way, it still gives us a count of 2 people per second, even though they spend a whole second moving. Is that okay? Now, if we bring it into the electronic perspective, this would be like so the other way is to enable 2 electrons to pass through the conductor simultaneously in a second. Okay, so now the question is, how do we achieve these things? How do we achieve these things? For the first case, we can do that by increasing voltage. Like I said, in the analogy of using human beings, if we make them run faster, then we can achieve 2 people passing per second, right? And by running faster, it means we have to increase their energy. So similarly, in circuit, if we increase the voltage, remember, the drift velocity is related to the electric field, right? So if the electric field increases, drift velocity is going to increase. And once drift velocity increases, the speed of the electron increases and more electrons can flow, right? Or the second case, we could just lower the resistance of that material. Is that okay? Or find a material with a lower resistance, and that will also allow more current to flow because they will face less what opposition. Okay. Now it is important to note that just as conductivity is not the same as conductance, resistivity is not the same as resistance. Is that okay? Resistivity, as usual, is an intrinsic property. Resistance is not an intrinsic property. Okay, because resistance is affected by the temperature of the environment, it's affected by the shape of the material, it's affected by the size of the material and all that. Okay, so they are two different things. Two different things. So this is a very beautiful artwork showing how these three guys work. And funny enough, all these people are human beings. All these units, they were named after human beings. Volt was named after somebody. Ohm was named after Simon Ohm, and Ampere too was named after somebody. It's just funny. Okay, so this artwork actually tells a lot, right? Volt here is trying to push amp. So amp here would be the current, right? To push the amp. And ohm, who would definitely be a typical Ghanaian, is trying to prevent him from moving, right? So resistance resists the flow of current. However, voltage's work is to make sure it pushes onto the current to move it. Is that okay? So basically this artwork tells a lot about what is happening. Okay, now we cannot mention these things without talking about Ohm's law. Okay, we have some 20 minutes, so I'll talk for the next 10 minutes and take questions, and we'll close today's session. Okay, now let's look at some things. I'm going to state some facts and build an argument over there, right? All materials that we know and components have some form of resistance, okay? Because we said conductivity is not perfect in materials. So if conductivity is not perfect, it means that materials have the ability to resist the flow, okay? However, there are a class of material called superconductors. They don't have any resistance. Is that okay? That means when current enters them, the current flows theoretically infinitely forever. Theoretically, okay? However, these are not things that you can have in your everyday circuits, okay? As at now, we can only create them in the lab, and it takes so much to create an a superconductor. So this is out of the way. We can't build regular electronics with them, okay? We can't. It will cost us so much. So yes, all materials have some resistance except superconductors, okay? So we can also say that all these materials or components, anytime electric energy flows through them, they consume some of this energy. So earlier, Emmanuel, you asked the question that why do the conductors heat up? The conductors heat up because the conductors themselves end up consuming part of the electric energy. Okay, that consumption is what manifests as resistance, and so current is reducing and all that. Is that okay? So every conductor, everything you would put in the circuit will consume some amount of energy, okay, from the power source. Now, sometimes it may be so tiny or so negligible that you can ignore it, right? But it doesn't mean that there is no consumption. There is always consumption. The wires that you are using consumes, okay, but usually they are not appreciable. They are very small. Is that okay? So each component consumes energy whilst it allows the energy to flow. Is that okay? Now, consider a very simple circuit. So we are creating a mental picture here. A very simple circuit, right? The energy demand of the load determines how much current will flow. We already said this in the previous lecture, that mostly the job of the circuit designer is dictated by the load, okay? It's the load that will tell you that, okay, you need to move this amount of energy and all that, right? We have already established that, okay? So since the different components are consuming different have different conductivity, right? It means that they all consume different amount of energy. Okay, so here we are talking about the energy consumed by the various components that makes up the circuit. Is that okay? So when these components consume energy, how do we see that the components are consuming energy? Remember, we said that the way we see, one way that we see that energy is moving is by the fact that electrons move or current moves, right? The same way, the way we see that energy is being consumed is the fact that this energy manifests around the component at voltage drops. So that's what we call voltage drop. So if you have a circuit, you take a multimeter and you measure the voltage across a component, right? That voltage you are measuring is the voltage that has been consumed by that component. Okay? Another way you can say is that it is the energy that component requires in order to move that amount of current through it. Is that okay? Now, this thing here is the statement of Ohm's law. Okay? Formally, we state it as the potential difference across a conductor is directly proportional to the current flowing through it, blah, 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 right? All that means that when energy flows through components, part of this energy is consumed. In fact, not part, the energy has to be consumed by the component such that by the time we get to the lowest potential, the energy is used up. Okay? That is what is supposed to happen. And that is basically what Ohm's law was talking about. Okay, so it says that for a component to pass a certain amount of current through it. Now, this is me paraphrasing, right? It would require a certain amount of energy, which is usually dependent on the resistance of that component. So this is me paraphrasing or rewriting Ohm's law in my own understanding. Is that okay? So formally speaking, we say that the potential difference across a conductor is directly proportional to the current flowing through it. Is that okay? However, this seems simple, but it is not that simple, okay? There are certain physical interpretations that we need to understand. Now, first of all, Ohm's law is actually a very fundamental principle in electrical engineering and physics, okay? You can do a whole lot of analysis with Ohm's law. It comes in very, very handy because it gives us a relation between voltage, current, resistance, okay? So it's very, very important, okay? Ohm's law was named after German physicist George Simon Ohm, who formulated it first, right? Now, technically, it's not a law, okay? It's not a law, but I won't go into that. Now, there are certain assumptions that Ohm's law also made. You should always say, anytime you are dealing with systems, you should always note whether there were some assumptions made. And in engineering and physics, we usually create a lot of assumptions. Engineers don't call it assumptions, they call it boundary conditions. Physicists will call it assumptions, right? But engineers will usually call it boundary conditions, right? So this thing would work so far as that and that, okay? So those things become boundary conditions. So far as you're operating within these boundary conditions, yeah, the system would be okay, okay? But they are still assumptions, all right? So this means that voltage, listen to something. This means that if the voltage across the conductor is doubled, right? If you look at Ohm's law, it's a linear relationship. So if the voltage doubles, current will also have to double. Now, take note that mostly for Ohm's law, we look at the resistance to be fixed. Is that okay? So the resistance is our constant of proportionality when we are dealing with Ohm's law. But take note that there are systems where current rather becomes fixed and resistance rather changes, right? There are systems like that, okay? So in Ohm's law, we assume a constant resistance, okay? So that means if voltage doubles, current will also have to double for the relationship to happen, okay? Now, take note that Ohm's law doesn't apply to everything, okay? There are systems that respect Ohm's law. We call them ohmic materials. Is that okay? Systems that respect Ohm's law. Not everything obeys Ohm's law. Other stuff do have their own way of doing stuff. Okay, now the SI units of resistance, we know its own. Voltage is volts and current is ampere. Now Ohm's law, you see this diagram that we have here, the only manipulation that you can do around Ohm's law, you can find it here. Okay, any manipulations. Right now we have seen an equation for power, we have seen an equation for Ohm's law, right? Any manipulations you can think of, you can find it in here. Is that okay? And Ohm's law is so important because it has become a foundational principle. Okay, if you are troubleshooting stuff, if you are analyzing systems, you will need Ohm's law. In fact, Ohm's law is invaluable, if I may put it. Okay, Ohm's law is invaluable. Okay, it provides basic understanding of how voltage, current, and resistance are interrelated. So that's the face behind the law. So basically, Ohm's law, I like to state it the other way around. V equals to IR. Okay, you see, in mathematics, there are meanings to stuff. Okay, in maths, when you write equations like this, we call something dependent and independent variable. So if you write Ohm's law like this, then it is almost like the current is rather dependent on the voltage. Okay, no, but in the statement of Ohm's law, if you actually study it critically, it is the voltage that rather depends on the current. Remember, the current is pushed by the source. Is that okay? The reaction between the current and the component is what causes the voltage drop. So I prefer writing Ohm's law as V equals to IR, so that mathematically it shows that the V is the dependent variable, the I is the independent variable. Anyway, it doesn't actually matter if you are just manipulating the mathematics around. Is that okay? All right. So another thing is that there are physical interpretations to Ohm's law. Okay. Now, in Ohm's law, we do mention of voltage. In our sources too, we mention voltage. Now, in our sources, we said that the voltage is the energy per unit charge. Is that okay? Now, this voltage that we are talking about is actually different from the voltage that Ohm's law is talking about. Please take note of that. Okay. Ohm's law is actually talking about voltage dropped. In other words, the voltage that has been used. Okay, voltage that has been used or voltage that has been consumed by that component. So in Ohm's law, the voltage that we are talking about is voltage drop, not the same voltage as our EMF. That's why some people prefer to call the source voltages as EMF, okay, making it sound or look different from the voltage drops in the circuit. Okay, so take note of these things. Okay, now take note that there are situations where for instance, if I have a 9-volt power source and a 9-volt lamp, I can just connect them directly. So technically, the voltage drop also becomes the EMF. Is that okay? So there is that situation, but the statement of Ohm's law is about voltage drop. It's not about EMF or the source voltage. Is that okay? All right. Now, so the voltage is correctly described as voltage drop, as in the amount of source voltage that is used up to drive the required amount of current through the component. So you see, technically speaking, the voltage that gets dropped is a reaction to the current that is flowing. Okay, that's how I like to interpret it because it makes sense in that way. Okay, so the voltage drop in a circuit is consequently the interaction between the flowing current and the resistance of the circuit. Okay, so every component has a maximum amount of energy that it can handle. Okay, it's like saying that everybody has the maximum amount of food he can eat. Is that okay? Just like that. So what happens if you overfeed yourself? Probably you have the experience already. Okay, so the energy consumed is usually converted to other forms of energy depending on the type of component. So if we are looking at something like a light bulb, then the energy consumed, if it is an incandescent light for instance, will be converted to light energy and heat. Is that okay? If you are talking about something like electric motors, then the energy will be converted to motion, mechanical energy and heat. If you are talking about sound, speakers, then mechanical energy and heat. So it's almost like there is always going to be a certain amount of heat that is lost. Is that okay? Always going to be a certain amount of heat that will be lost. Okay, so as I said, for light bulb we have light, energy, and then heat. By the way, what is the difference between heat and temperature? Find out and give me an answer tomorrow. Okay, all right. Okay, so when the energy of the source is increased, it would cause more current to flow, which also means every component in the circuit would have to adjust itself to allow that current to flow. Okay, so in that case, if a particular component is not built to handle that amount of energy, then it burns or catches fire. Is that okay? So this would lead to components working beyond their rating, building up heat, and eventually breaking down. Okay, so for this reason we need to understand these fundamentals so that we don't burn people's stuff, right? And from the behavior I know from electronic system designers, when they burn something, they don't own they don't own the faults. They say they blame the component. Meanwhile, the component didn't supply the energy. You supply the energy, right? So I don't want you guys to be burning stuff. So that's why I'm taking you through all these concepts so that you gain why and knowledge in why these things do happen. Okay. So it is therefore important to ensure that the circuit operates in what the right condition. You see, it is normal like that in this world. If you don't operate things at their rating, they break down. Even your body. If you don't treat your body the way you are supposed to treat it, you break down, you fall sick. Is that okay? The same thing happens to. Now, the third scenario, this is third. The first one was no connection between. The second one was we connected a bulb between. Now, the third one is instead of a bulb, we are connecting another copper wire between. So we are bridging the copper wire from the anode to the cathode, right? What would happen when we do this? Okay. So the question is, what happens when the anode copper is connected directly to the cathode copper without a load? Probably some of you already have an idea of what will happen, right? Now let's go through. Now, take note that the electrons separated from their parent atoms resulting in positively charged, forget about this. Let me go my freestyle. Okay. So already we said that the chemical reaction stripped electrons from the anode material and embedded them on the cathode material, right? Unfortunately, these electrons can't return through the battery. The only way they can return is through an externally connected path or conductor or wire, right? So the electrons actually want to go back because that is their default state, right? But then they can't. Now, they can because there is a barrier preventing them within the battery, and we have to physically connect a wire from the anode to the cathode for them to do that. Is that okay? Hence, when we connect a copper wire without any load, what happens is that we have created what in physics we call a path of least resistance, right? A path of least resistance. A path that the electrons can travel without encountering any much resistance. That means the electrons are going to move at a very tough speed and something else is going to happen. Okay, so when this happens, a very large amount of these electrons are going to drift because there is nothing in there to oppose them. The only opposition they will feel will be the copper's, the copper wire's resistance, which is actually very small. Okay, so that means the electrons will move at a very high speed, okay, from the anode, from the cathode to the anode, okay, and this will constitute a very large amount of current flowing. Is that okay? So when we do this, the first thing that we've seen is that there is going to be a very huge amount of current flowing. Is that okay? Now, when this current arrive at the anode, okay, they will rebound to their parents. When they rebound, remember they were traveling at a very high kinetic energy, right? So if they rebound, that energy has to be given up. Now, chances are that the atom is going to absorb that energy. When the atom absorbs that energy, that is not its state. The atom itself becomes excited. And when an atom gets excited, what happens is it vibrates. Okay, so the atoms will vibrate, and this vibration we actually quantify and call them as phonons, right? Probably you have heard of photons, but there is also phonons, but I'm not going to go into that. Okay. Now, as these atoms vibrate, okay, they lose the energy through heating. They give up that energy. And where do you think that energy will go? The heat energy will be felt in the material. Okay, the atoms vibrating will cause heating in the material. So the second thing that we're going to see is that the conductor is going to heat up as a result of the lost kinetic energy being converted to what? Heat energy. Is that okay? So if the copper wire that you have used is not thick enough to withstand this heating, trust me, what you would see is that the insulation around the copper wire will start melting, and even depending on the amount of energy connected, the copper wire itself will end up burning. Is that okay? So three things: a large amount of current would flow, there will be heating up, and occasionally burning if the energy is so much, right? Now, this is what we call short circuits in electronics. This phenomenon that I have explained is what we call short circuit. Okay, the last time you connected something and it caught fire, chances are that something short circuited. Is that okay? So be careful about this. Now, what happens to our battery when a short circuit happens? Let's look at that. I think we will close on that note. Okay, now we should recall that our battery has a positive ion core and negative ion core, and we need these ion cores up and running to sustain the field, right? But this is the situation where the electrons are moving back to recombine with these ion cores. That means the negative side is losing those extra electrons, okay, and becoming atoms. Now, when these extra electrons go back to their parent atom, it will neutralize their charge, okay? But we need these charges to maintain or sustain the electric field, right? So short circuit ends up collapsing the field. Now, physically, when short circuit happens and you use a meter to measure the voltage of the battery, it's almost close to zero. You get something almost close to zero, if not zero, okay? This tells you that when short circuit happens, physically it breaks down it collapses the field. Is that okay? The field that we are dealing with collapses the field. So this is why short circuits always leads to a maximum drop in voltage to almost what? Zero. Okay. But then if voltage has dropped to zero, and we know that we need voltage to drive current, why then does current still continue to flow even when there is short circuit? All right, think about this. I'll answer you in a moment. Okay. Now, simultaneously, what is going to happen is that the battery tries as much as possible to sustain the charges, right? And we saw earlier that the way the battery sustains the charges is by causing more chemical reactions to happen, so that electrons will be stripped off from the cathode and deposited from the anode and deposited at the cathode, right? So while this short circuit is happening and so much current is moving, the field is collapsing, the battery also kicks in, trying to increase its chemical reaction in order to sustain the electric field, right? So in so doing, what happens is that the moment any electron is released, is pulled from the anode to the cathode, the moment it gets to the cathode, that electron goes back again to the anode, because there is a short circuit path there, right? So it means it's almost like the battery, it's almost like you are fetching water into a sieve, right? you put the water in, all right, but the moment you put it in, it drains again, right? So that becomes something similar to what will be happening to the battery. The battery will try to keep up with increase the chemical reaction in order to sustain the field, but then the moment it releases the electron to create a field, it neutralizes. Okay, so the chemical reaction will proceed rapidly, and what will happen is that eventually the battery will run out of the material, because the materials in the battery that causes the chemical reaction to proceed are finite. Okay, there are finite amount of material, so the chemical reaction cannot proceed for eternity. Is that okay? So we have explained two things. The reason why electrons still flow even though the field has collapsed is because the battery tries to keep the field, and the electrons that are released keep drifting away. So those electrons are what we still measure whilst the field has even collapsed, right? And why does the battery run down quickly when there is a short circuit? Is because the battery tries to keep up or sustain our field by causing more chemical reactions, and in the course of that, it depletes the chemical element that cause the reaction to proceed. Is that okay? So in a nutshell, what happens is that the battery heats up because of the rapid reaction that goes on. Now, some textbooks will explain this as the battery heats up because of internal resistance. Well, from their perspective, that would make sense, right? But then, I mean, technically, the battery, there is that gap, right? The electrons don't have that continuity. Okay, something is happening within the battery that is causing the electrons to be emitted. You get the point? So to say that is because of the internal resistance, well, we can just simplify things by just assuming that the battery has an internal resistance, right? But I think that what is really causing the problem is the fact that the battery trying to keep up the field by causing more reaction to occur. In so doing, it depletes. Now take note that chemical reactions proceed and release energy in the process, right? So this energy, part of this energy is what ends up warming up the battery. Okay, because probably the battery is not built to withstand that number of reactions occurring. Okay, so that is what I think. And so yeah, if you have any kind of recommend suggestions, you can put it in the comment box down there. All right, so short circuit, although it's not an ideal, well, so this is what happens during short circuit. So during short circuit, you realize that your battery will run down fast. I've given you the reason why. You realize that the battery warms up. I've given you the reason why. You realize that the conductor, which is your wires, heats up. I've also given you the reason why. So now we know what happens during short circuit. Okay, now you see, short circuit is a bad thing, but it actually has practical applications, right? For instance, if you are using an electric iron in your house, the electric iron is basically causing short circuits. Okay, now the heat that is generated out of this short circuit, the material of the iron's element has been chosen such that it has a very high melting and boiling point. So that heat is actually not enough to destroy it. Okay, but basically what happens in an electric iron is short circuit. Okay, through short circuit we start fire, and controlled short circuits are used to cause ignitions and fire ignitions and all this kind of stuff. Okay, so yes, we have practical applications for short circuits, heating element, ovens, pressing irons, incandescent light. All these things are basically going through short circuit, though you can argue that those resistive elements have higher resistances. So basically those higher resistances can serve as load, right? But basically we have short circuits in there. All right, so for this heating element, the material that are used to build them have high melting and boiling points such that they can withstand that energy build up during the short circuit. Is that okay? So yes, I would end today this evening session here. I think we've already consumed our time. We still have a few things to cover on this lecture. Like I said, this particular PowerPoint contains about 90 stuff, right? And 90 slides, so they are quite a lot. Okay. All right. So that is the end for this session.